Most AI coding sessions start with a vague instruction. The agent immediately starts pulling up files, reading test routes, and searching the repository. We usually evaluate this step by watching the terminal logs. If the agent opens a lot of files, it feels like progress. Teams often dump hundreds of raw search results directly into the agent's context window, hoping the relevant data is somewhere in the pile. Then the execution derails. It modifies the wrong module, hallucinates a dependency, or misses the architecture entirely. The immediate assumption is that the prompt was wrong. Engineers will spend hours tweaking the exact phrasing of their instructions. They rewrite the prompt, trying to force the agent to behave, completely ignoring the fact that the actual data pipeline feeding the agent's memory is broken. Activity is not execution. An agent can spend 20 minutes reading unrelated files and old documentation. It creates a convincing terminal output, but the work is not converging on a solution. Giving an agent access to the entire repository doesn't solve this. It compounds it. It gives the reviewing manager a false sense of security, assuming that because the agent has all the data, it will naturally find the right path. Managing AI coding work by terminal vibes and confident summaries creates an illusion of control. The actual code generation is left to luck rather than rigorous engineering. Engineering leaders must treat context selection as a strict information retrieval problem. This requires a transition from the subjective art of prompt engineering to a measurable data discipline. The goal is to map the repository graph, isolate the dependencies, and extract a bounded context bundle for the specific task at hand. Success in this field relies on quantifiable mathematical scoring. We prove that the selected data matches the engineering intent before the first line of code is ever written. Applying these metrics to AI coding sessions strips away the guesswork. Managers can stop asking if the prompt felt right and start looking at objective telemetry about the data the agent consumed. This enables teams to track the utility of the context bundle by measuring the exact quality of the agent's starting memory. Controlling an AI agent requires proving the quality of the map it was given before it started driving. Measuring the success of that starting map requires waiting until the journey is over. The evaluation must happen after the coding session is complete. Engineering tasks evolve. A session might start as a simple styling update, but midway through, the agent uncovers a broken route or a missing test suite. The required context shifts as the real work gets locked in. So we look to the absolute truth of the session, the final code diff. This is the exact set of files the agent actually modified to solve the problem. We start at that finalized diff and work backward. We take the final engineering reality and compare it against the starting theoretical assumptions of the context bundle. This backward analysis isolates the single most critical variable. It answers the question, did our retrieval system actually give the AI the specific files it needed to write this code? True system measurement tests what the AI was given against what the AI ultimately built. This diagram shows two datasets. On the left, the context bundle. On the right, the code diff. Their intersection is recall, the percentage of changed files successfully predicted. When recall is low, the overlap shrinks, meaning the agent was starved of necessary architectural files. You will see this immediately in the logs. The agent has to halt its execution and start manually exploring the repository, attempting to find the pieces the system failed to provide. That search process carries heavy operational risks. The agent loses track of the original dependency path, increasing the likelihood of architectural drift, missed test updates, and silent failures in related modules. An agent provided with high recall context behaves differently. It starts with a comprehensive map and executes deterministically, moving straight to implementation. A low recall score indicates the agent was flying blind. It proves the context pipeline failed to secure the full scope of the required work. Recall is only half the equation. We must also measure the red area of this diagram, the irrelevant files. This is precision, the percentage of the provided bundle that actually mattered. If precision is low, noise dominates, stuffing distractive files into the agent's memory. This carries a direct financial cost in wasted tokens, but more importantly, it dilutes the AI's attention span. The agent is forced to process huge volumes of text that have no bearing on the task. This excess noise directly causes hallucinations. The agent reads an outdated module or an unrelated feature set included in the bundle, and wrongly attempts to wire those concepts into the current code fix. Giving an LLM raw, uncurated repository access is a disadvantage. When the data lacks structure, it becomes an active hazard that derails deterministic logic. Low recall starves the AI, while low precision drowns it. Expanding the context window is never a substitute for accurate, precise curation. There is an important exception to strict precision tracking, shown in this spectrum from highly targeted tasks to broad radar sweeps. If the task is isolated, the context bundle should be highly constrained, keeping the precision score near 100% on the left. But if an engineer requests a broad architectural audit of the entire security layer, the agent must read and analyze dozens of files to understand the system, even though it will only ever edit a handful of them. In that scenario, a drop in the formal precision metric is not a system failure. It is the expected signature of exploratory research and comprehensive auditing. Raw numbers require interpretation. The metrics must always be contextualized by the original engineering intent to serve as a reliable management signal. This chart shows what happens when we apply these measurements systematically. By tracking recall and precision across hundreds of coding sessions, abstract theory is converted into actionable telemetry. Engineering managers can stop guessing why an agent struggled. They can look at the historical data and pinpoint exactly which areas of the repository consistently fail to generate accurate context bundles. Measuring this quality loop allows the underlying retrieval system to learn the specific file relationships within the repository graph. Every measured session improves the accuracy of future bundle predictions. A team armed with this data operates with a clarity that isn't available to teams manually scrolling through terminal logs to decipher their agent's behavior. Continuous measurement creates a compounding advantage. It lowers costs of future iterations, reduces the senior review burden, and isolates systemic context failures. The entire AI workflow improves systematically only when the quality of the context bundle is treated as a trackable engineering signal. Engineering leadership is moving toward a new requirement, mathematically proving the agent received the right context, rather than hoping the output is correct. By enforcing strict telemetry for recall and precision, leaders force their AI tooling to provide an auditable, evidence-backed story of its own execution. Context selection is an information retrieval problem that must be judged by the final reality of the code diff. Improving AI context is impossible without first measuring whether that context actually helped the agent complete the task. Effective AI engineering management requires proving the agent navigated from an accurate map, rather than limiting the review to the code produced by the machine.